Hello everyone and welcome to Software Engineering. Today we're going to look at the topic of Docker and containers. I'm excited to share this. I think Docker is a breakthrough technology and it really eases deployment pain, software building, running deployments. And I think as we learn this together, I think it's going to open up some exciting opportunities in your minds for how you deliver software. And quite literally, it has the potential to change the way we think about software and the way we deliver it to customers as well. It's been described as one of the most important pieces of software ever written. And we're going to talk a little bit about the topic of containerizing as well. We're going to show you how to work with Docker, particularly their build, ship, and run mantra. We're going to look at multi-container applications. We're going to look at Docker Desktop, Docker Compose, Docker Swarm, the whole motivation for Docker, so why Docker. We're going to look at the architecture of containers. And also we're going to talk a little bit about Docker images in DevOps pipelines, although we have a couple of lectures on DevOps coming up where we will do that as a deeper dive. Today we'll focus on some basic Docker commands, what Docker can do for you, and how to get running with this technology, basically. So that's today's lecture. So firstly, you might think, well, Dockers, are they a bit like virtual machines? And it's easy to confuse the two. It's an easy connection to make that Dockers and VMs are somehow related. They do have fundamentally different architectures and also different benefits. And they're really addressing different needs. In fact, it's possible to run Docker inside VMs, and we'll look at a couple of use cases where that happens. You can think of it this way, that a complete house has everything that it needs to sustain itself. It has buildings, heating, plumbing, the infrastructure, the building is all there, the foundation's all there. A VM is a bit like that. It has everything it needs to run. It has an abstraction of the operating system, the file system, everything you might need. Whereas you could consider a Docker container as like an apartment in a bigger block. So the apartment is using shared infrastructure, it's using shared heating, shared resources, and these containers are like blocks, apartment blocks within that bigger block context. So for that reason, containers are considered like a thinner architecture than VMs, and you might hear terms like thin client or thick client. Often that refers to the tech stack that's used to build and deploy. Whether you're building a VM, that's kind of a thicker architecture compared to a container, which has this slightly thinner structure. So they're different but not mutually exclusive. You can, as I say, run Docker on a VM, and that's what you're seeing on the right-hand side, where with app 7, you're running binaries and libraries on an OS together alongside Docker, which maybe is running on the Linux operating system with a Docker engine and binaries and libraries on top of that. You would also have a hypervisor and a physical server running that architecture, whereas on the left, your data center is basically running the physical server, the OS, and Docker as the thin client on top of that OS, and then running app 1, app 2, app 3, perhaps in 3 separate Docker containers on the left, or one bigger Docker container. Both architectures are possible with this Docker deployment and the topology of Docker, if you want to consider it that way. So Docker's mantra is build, ship, and run. And as I say, it's one of the most exciting technologies, I think, ever to have been released. We're going to look at creating Docker containers. We're going to see a couple of practical examples. And their whole motivation is, and sort of mantra is, build, ship, run any app, anywhere. And the idea is that I can go from dev to ops. So this is a bridging technology for DevOps, dev to ops. And literally any software that you like can run in a Docker container. So we've listed a few here like Java, C++, ASP.NET, JFrog Artifactory, Conan, you name it, curl, MySQL, WordPress, all of those you can run as containers sitting on Docker. And it will work on any OS as well. You can run it on Windows or on Linux or on Mac. And physically, you can run it on these machines, as I'm doing here, or you can virtualize and have this running in the cloud as well. So Docker is write once, deploy anywhere. It literally is that kind of power. and it will take you from dev to ops. So it will take you from being a developer to being like a software creator, able to deploy apps to the ops side and bring that bridge from dev to ops together. Build, ship, run. Because as software engineers, it's not just the ability to create code that's important, it's the ability to deploy solutions. And really you can see Docker as the solution deployment engine to carry your code and compiled applications to your customer via that deployment. Do check out docker.com/enterprise for enterprise licenses of Docker and how to build scalable infrastructure using Docker. Here's some vocabulary for you. So a Docker image is the basis of a Docker container, as we call it. It represents a full application. A Docker container is the standard unit in which the application service resides and executes. And the Docker engine is what we use to create, ship, and run Docker containers, deployable on a physical or virtual host locally in a data center or a cloud service provider. And then we have the registry service, which is called Docker Hub or Docker Trusted Registry, and Docker Desktop, which is what I'm going to show you, also is part of this registry service if all of your containers are registered locally and running locally. So registry service will give you the ability to run cloud or server-based storage and distribution services for your Docker images. So here's some basic Docker commands. I'm going to switch to the command line console. We're going to try a few of these out. Here I'm using WSL, which is the Windows subsystem for Linux. I'm on a Windows machine, but I have a kind of like a Linux terminal. It itself is like a VM running inside Windows. If you're using Windows, you can actually just install WSL from the command line by going to the Start menu and typing WSL, and it will launch the Windows subsystem for Linux for you. And if I just start by typing docker -" version, you can see that Docker is installed on my machine, and it's at version 27.03, which is reasonably late, quite current. And I've got various commands now that I can run. For example, if I run Docker images, it will give me a listing of images that I have installed and available locally, coming from Bath University or from open source solutions or from proprietary containers. You might be interested to know, those of you who are doing AI or interested in AI, that the OpenDevin AI agent is delivered as a Docker container. We'll have a look at that as well if we have time. And you can literally pull that down as a container, run it, and be up and running with an AI agent in minutes. So Docker PS, we just run, Docker images is the first command that we've run. That gives us the list of containers we have available. We could also do Docker PS, which will give us a list of processes which are running on our machine. You can see I've got a Docker agent, that the all hands agent running on this machine already. And I can pull images from open source repositories. So if I did a Docker pull on, for example, MySQL, I'm probably up to date because I did this recently, and it will get the latest from the Docker container library. Same for tools like WordPress. These have all been encapsulated into Docker containers, and so I can pull those images down from open source repositories really, really easily using the Docker pull command. I can stop a container with the Docker stop, or the Docker RM I can use to remove, or I can use Docker RMI to remove a particular image. The special case of Windows has what we call a Docker container registry running locally. I'll just flick to that so you can see. That is the Docker Desktop. And this gives us containers, images, and volumes. And just going back to that terminology, we can see we have some high-level containers running, and the source of those containers, i.e. where the repositories are getting from. I can actually start and stop containers from this interface. I can also view vulnerabilities of each image, and I can view the commands that have been used to construct that Docker container as well. So this is basically my management portal for Docker on Windows, and similar software exists on Linux and Mac. And I can also see my container usage. So I can see who's using what and what containers and volumes I have. On the volume tab, I can see that I have these containers, and these are in use at the moment by different parts of my system. And I can see the builds as well, that I've actually run a Docker container, and I can see the various states of those builds as well. We'll come back to that and look at more of the analytics in a little bit. First of all, I want to get us started with a simple Docker container. And after looking at these Docker commands, I want to start with how to construct a Docker container. So let me just explain what you're seeing here. This is a Docker file, and we give a Docker file to Docker with the -t build option, and Docker will build a container. And essentially, this is the make file, the recipe that's used to construct the Docker image. So line 2 of this describes that base image. And Alpine is one of the most common base images that we give to Docker. So that's our base image. We're going to pull from the latest Alpine image. We could also use Ubuntu. Ubuntu 2004 is a good latest image to use as well. In fact, I use that in some of my examples later. Then line 5, we're going to run APK to add and install Python and pip. So the two tools, which will then be added to that base container image. And so now we're starting to add the tools that we want our users to use. And at the same time, because this might be an out-of-date version of Python or pip that we're installing, we're going to run, and you can see this Docker command run. These commands look like the native commands that we might use on Linux or Windows. Run pip install -- upgrade pip is going to run, or it's basically going to call pip recursively to upgrade itself to the latest version of pip for the Python installer. And then line 11 here is copying from a local requirements.txt to /user/source/app. And then line 12 is running the pip installation program to build and install those requirements directly into the container. And line 15 is then copying the app.py that we want to run to the user source app in the container. And templates index.html is getting copied as a destination to the app templates directory. And then line 19, we're going to expose port 5000 to the host, and that means that we can access data through a web service. Port 5000 will be available, that the container will expose to the host. And so this is a great way of building and deploying web apps, and you want to, or web services, API endpoints as well that people can connect to. And then the last thing we do in this Docker file is we run the Python command on the app that we've copied into the container. So it's important to optimize our Docker file. We'll see why shortly. If we're doing lots and lots of intensive copying commands, it's best to do that once, and we'll see an example of that as well. So let's switch to a little bit of motivation, why we would want to abstract things into Docker. So here I have a handwriting.py Python script, and you can see it's using NumPy, which is the machine learning library for linear algebra to help train our model. And it's a very simple script. It uses sklearn, which is another dependency that we have, a Python library dependency. And it uses the MNIST digits training data set to load basically a load of handwritten images of numbers that people have typed, and that's the training data. And then this line will split the data into training and testing sets. And then we apply a simple logistic regression algorithm. And then we're going to predict a particular value from our images. And then we're also going to calculate the accuracy of the model and print the resulting accuracy to the console. And then we're going to plot an image, and we're going to ask for the predicted label that the model predicts that image should be. And this is a very simple script. I've actually installed the dependencies already, but I could just run Python and then handwriting.py. And you can see here that I've got a situation where Python's not found, okay, because I started a new terminal. And this is one of those annoying things that somebody's given me a script, it works on their machine, but it doesn't work on my machine. And this is one of the motivations for Docker. We want an environment where things like the path, the dependencies are kind of all set up for us. So in this case, I've now got to go and laboriously, manually set up my own path to be able to run Python. Imagine a non-technical user having this problem. They now have to go and contact support, and it slows down the usage and adoption of your software. If I'd have put that into a Docker container, I could have set that path up automatically for usage. So now I've manually added the path, and it predicts that this image that you see here on the screen is the number 6, and you can see it's correct. It is the number 6. And so the model is predicted with an accuracy of 97%, and the predicted label is 6. So that's all well and good. How can we put that into a Docker container? So let's switch to our console, and I'm going to work on a mounted drive, and I'll explain why that's needed later for persistency. But I'm going to start with a Docker file, and the first line of the Docker file is telling Docker that we're going to use Ubuntu as the base image, which is great. And then I'm going to run a bunch of, so my environment is using Debian front end, and I'm going to use the non-interactive version so that I avoid prompts during the installation of the Docker image. And then you can see this command. This is running all of these programs here to install the applications that I want to be available in the built container. So in my case, curl to access web software and install it, wget, unzip, the open JDK for Java, CMake, which is a C++ build system I want to use, nano, vim, and software properties, and sudo. And then I want to also install VS Code in this case. You can see here that I'm running wget to install the VS Code editor, and I want to add a user called demo to this software, and I want to then create that user demo and give him some rights, put the password into sudo. So again, all of this I can configure now into the VM, and I'm going to then set the work directory to be /home/demo. I want to copy my files for installation. In this case, CPP test is the executable software testing tool from PowerSoft that I want to be available to my users. ISO-aglib is the software that I want to build in this particular container. And then I run gzip to unpack the CPP test gzip tar file, and ISO-aglib as well goes through the gzip, passing to tar to unpack into that home/demo directory. And then the pain that I experienced of having to set up paths manually, I want to configure so that I can actually avoid that, and so I can actually set my environment variables up for the user's convenience. I can actually set the path using this command that the home/bin directory is then set to be in my path. Then I go back and I switch back to the demo user, and I run the build to run the tool to build the software that I want to deploy. So that's kind of one example of a Docker file. Another example would be a simple Docker file. We can start with this, where we actually use Python 3.9 as the base. This is to run my handwriting script. I have a working directory of app. I copy the scripts to the current directory of the built VM, and then I run this dependency or this command to install the dependencies in my Python script. So numpy, skykit-learn, and matplotlib are my dependencies. This command will install that into the VM, into the Docker container, and then my command is to run that handwriting script. So what I'm going to do is I'm just going to move the first Docker file and just call that the CPP build. That's to show the more complicated C++ build. And I'm going to move my Docker simple file to the Docker file. So I'm going to tee up this as being my first Docker image. And so if I look at my Docker file here, I'm now going to build this as a Docker container. And I do that, if I do Control R on Linux, I can get reverse search and I can go to previous Docker commands that I've used. And I'm going to do Docker pull, Docker ps. And what I'm going to do here is Docker build. And I'm going to create an image called Bath University handwriting image. Okay, so let's just give that a shorter name, and that will take that Docker Compose file and it will build for us our first Docker container. Okay, so it will copy the script that I've got locally. It will install those dependencies for us so that our users don't have to, and it will build that container with those dependencies. And then it will run that script as well with our Python command that we've also installed into the container. So it's absolutely amazing. It's abstracting all that work for us. It's automating that work of gathering the things that we need. So if you've got complex software that you're building for your projects, think about Dockerizing, like put all the dependencies into a script, build a Docker image. I'd love to see Docker images being delivered as part of the coursework. It's so much easier to run and to see how you've constructed and built your software. So as you can see, this command has taken a while. Again, you doing it in advance means that the user doesn't have to. You can deliver a built image that they can run, and it will have all of those dependencies already in the Docker container. And so this has now created an image called Bath University handwriting image. If we go to our Docker registry, you should actually see this appearing in the containers and in the images. So now we have Bath University handwriting image, which was created 18 seconds ago. And you can see it's quite big. It's like 470 megabytes because it's an image that basically gathers and compresses all of those dependencies that we have to run our handwriting recognition script. So looking at this, you can see how it was built. There's 14 layers, what we call layers to this Docker image, where we ran those installations, upgraded pip, ran Python, all of that. So that's been successfully built with the docker -t build command. We're now going to run that container image, and it should also have a link to the container itself, which we're going to now run. So let's go back to Docker. That's the build command. I'm just going to go and do Docker run now. So this is Docker run, and let me just get the text right. And it's just, if you're ever unsure, just do history grep Docker run, and it should tell us. Okay, so I'm going to repeat Docker run, and this is the syntax of Docker run. My name I'm going to give it is Bath University handwriting container, and I'm going to run it with this image. And the latest tag is just saying, please pull down the latest image from that container. And it's given me an error that the Bath University handwriting container is already in use. So I'm just going to give it another name, handwriting container, and that will create a new instance of that container for me. The other option would be to run that container, to remove that container and run it with the same name as well. And now you can see it's basically gone into that container, it's run my script, and it's returned the accuracy of 97% for that predicted image of 6 from the NIMST data set for handwritten images. And that has all been running in the container directly. So I didn't need to set up any paths. I could just run it, I could build it, and I could deploy it, which is absolutely amazing. So let's run the more complicated example. So here I'm in my Docker file. I have the Docker CPP build. I'm now just going to move the Docker file that I've just created and call that handwriting, and move my Docker file CPP build to be my main Docker file. This is because Docker takes as its argument the Docker file command, and I'm going to just run it as it is. and we'll see that it will fail at a couple of points when something can't be found. I want to show you a little bit about debugging a Docker file. So I've deliberately put a couple of errors in this script that we can then use to debug. So once again, I'm going to go Docker and I'm going to build this time a new image. And this is going to be my C++ Bath University Software Engineering C++. We can name the containers as we like. And this is now going to go and try and build those C++ containers. And you can see that it's failed in this case because I didn't give the tar files and the isoaglib project files to the Docker container. So what I'm going to do is I'm just going to go and create those from the installations of the tools that I want to install. So the way I do that is I have C++ test here. I'm just going to create tar files, and typically with Docker we use gzip tar files for installations of programs. So tar takes as its argument CVF, and we're going to create cpp test.tar, and I'm going to pass the cpp test directory. We're basically going to zip up the whole of this installation, and we are then going to compress it, because containers can be quite inefficient when they're processing lots and lots of files across the container registry. So where possible, we want to use gzip and tar to compress things, and it's much more efficient to uncompress files inside the container rather than to copy, in this case, millions of files across the Docker infrastructure manually. It's just an efficiency issue. So while that's happening, no need to wait around. I'm also going to zip the other file. And again, I'm going to start WSL and a WSL terminal. And I'm just going to tar cvf isoaglib.tar, and I'm going to tar up the isoaglib. Again, preparing the software that I want. This could be you could also do a git clone inside the Docker container, which I've seen many people do. Either copying physically or git clone would also work. Of course, I'd have to then install git client into the container first before I call git. But now I have, if I look at my tar.gz files, I have the compressed images for Parasoft and also for isoaglib, and I'm going to actually it's just the tar files that I have at the moment, the two tar files, cpp test and isoaglib. Let me just compress those, cpp test.tar, and I'm also going to compress isoaglib.tar. So you could consider that as a pre-processing step. Get the files that you want to copy into the container, but zip them up, as I say, because it's much more efficient to copy the zip file once into the container. And that's what you see in VS Code here. If I go into that directory, you should see in my Docker container, my Docker file, where I install all of these dependencies. I could also say install git into this dependency. And then here, when I'm doing a single copy of a large amount of files that I've just tarred and compressed, gzipped compressed, to copy into the directory, and then I will unzip them and untar them once I'm inside the container. And we do that, as I say, for efficiency reasons. So now that should be gzipping. I'm going to go back to my Docker command here, and I'm going to go to my mounted directory. And I'll explain why I'm using a mounted directory. That's for persistency later. When you use Docker images natively, the directories don't persist. So you create your Docker image, do some work, and then you destroy the image. Nothing persists after that. Of course, normally we want to have a shared data area where multiple Docker containers can write to and read from a shared network drive. We call that persistency. So I will talk more about that later in this lecture. But for now, we've got a mounted drive called MNT Work Bath Docker, where we're actually storing all of these files. So I'm going to just move the compressed files that we just created .tar.gz. I'm going to copy that here. And you can see the volume of that installation is quite significant. I'm also going to do the iso-aglib .tar.gz here. And I think once we've done that, we are now ready to go. And that error message that we received when we tried to build the Docker should now go away, because those two files are sitting at the same level as our Docker file. So our Docker file says copy cpptest.tar.gz, copy iso-aglib.tar.gz. That is what these two lines are doing here in the Docker container. Okay, so we're going to run Docker again. Hopefully we fix that issue. I'm just going to do Docker on the build command, and I'm going to do Docker build once more, and just try to find the previous command. Docker build, and we're going to call this Bath University Software Engineering, and let's call this CPP test. And now that's going to go and read that Docker file and build our container for us. Now you'll see that building Docker containers is not a trivial exercise. However, if we follow these steps, we want to install dependencies, install the files that we want to work with, and then a third step is usually to install the build commands that we want to run. And then once we've done those three things, we have something that we can deliver to our customers. Now you can see these operations are running much faster. Copy of those gzip tar files. That only took a few seconds, but we are now unzipping them in the container. And that's going to take a short time to unpack everything that we've basically just copied over into the container infrastructure. And you'll find that that's the step that really takes most time when we're building Docker containers. And Docker helpfully actually shows you the time each step takes, so that if you want to optimize, if you need to optimize later, then you easily can do. Okay, so that's going to go through. It's going to run our gzip, and we're going to go into the container, and we're going to see that we will have everything that we need in the path, and everything will work quite well. You can see some issues have been created, some problems have been created here, that our build of the tool didn't work. However, I think the container should still work. Let's just do a Docker run. So Docker run here, and we're going to go and we're going to name this as a C++ tester. This can be named anything we like, and we're going to run the container that we've just built, which is in our case, we just do a history. It's the Bath Uni Software Engineering project, and I'm going to do a grep history piped into grep Docker run. Okay, and we need quotations for that. And now we can see this is the run command to run a particular image. And so we're going to do Docker run here, and we're going to name the image PowerSoft container, CPP for example, and then we're going to give it the command, the container that we've just built. Okay, so the container we've just built is called Bath University Software Engineering C++ test. So we pass that as a final argument. Now you see there is an issue. It was unable to find that latest image because it didn't fully build the Docker container. So let's go into a further debug session. The actual command that failed to build, if we go back up to the top, was the final step, step 13 of the process from memory. And I'm just going to basically remove that from the Docker file. There's a CMake command here, and I'm just going to essentially comment out this run step, and we'll come back to that just to see if we can get the container building. So let's go back. We're going to do Docker build again, build that Docker image, and it once again will rebuild all the steps that we've taken in that Docker compose file. And it should be ready in about 20 seconds again. So you can see there's quite a lot of debugging. If a particular step fails, comment it out for now. Get the simplest container working. You can see now that's actually worked, and we've exported the layer that's been created to our Docker container registry. We should now have something in our Docker container registry called Bath University Software Engineering CPP test. So let's go to Docker and our container, and we should see, there we go, there's our new Docker container ready to roll. So now I'm going to enter the container, and basically we use Docker run for that. So again, I'm using my history, and I want to do Docker run here, and I'm going to name this container as Parasoft container for C++. So I'm just going to copy that, and then the final argument to Docker run is the name of the image that we want to run, so Bath University. It does tab completion, so if you complete on here, you can get software engineering CPP test, and you're asking it to pull the latest that we've just published, and that should now run the Docker container. Indeed it does. We are now inside the container here, and you can see this is now user demo, which is what we created in the Docker file. So we created a user called demo. I'm now all set up, and you can see I've got my CPP test installation. So I could actually run CPP test CLI, and it will run the commands because they're already in my path. And you can see if I just echo the path, it's correctly set it up for me that my CPP test and my CPP test bin directory are all set up for me and ready to roll. It's absolutely fantastic that I now could deliver this Docker image to somebody who needs Parasoft and ISO-aglib and wget and all the software that we've already installed. And there you go, there's the container with everything all set up. So there we go. So that's now working. The final build step we will debug at a later stage, but that is essentially just checking why our ISO-aglib project didn't build. Once we found the correct build commands, we could also add that to the Docker file to complete that third step. So now, hope you're getting excited, because we have two Docker containers, one for the Bath University handwriting AI model that we've just built, and one for developing and testing safety critical C++. Two separate images built 10 minutes apart, could deliver to two different customers. And that's the power of Docker, is that you abstract into containers, deliver those containers, and it just manages the process of the delivery for you. And you've got containers now that are running that people can connect to, people can do software builds on, and it's just so powerful. So let's go back to the slides and just review what we've done. That's why I put here, important to optimize your Docker file. The copy commands can be quite intensive, as we've seen. Make sure that those are as efficient as possible by using gzip and tar before you do copies of large data. We've seen Docker build to build the Docker container from a base image. We've seen Docker pull and Docker push to push a particular image, although the push command is actually automated by Docker run. In my case, when I did Docker run, it pushed the container to my Docker desktop, and there I didn't need to actually do that step manually. Sometimes you do. And so putting it all together, we are linking dev and ops. So DevOps is the name of the game. Developers are building their development environments. They're building from the dependencies. They're creating the files that they need. Then they're shipping. They're creating and storing images. And then they're deploying, managing on cloud infrastructure or locally or on virtualized environments, the Docker containers. And so I hope that you get excited about building and delivering Docker containers. As we've seen, that first base image of Alpine or Ubuntu Linux, I think I used Ubuntu as my base image in the first Docker file. So this has used Ubuntu 20. And then I used the Alpine image and just a basic Python base in this case. So it defaults to Alpine. You have to specify if you want to use Ubuntu, which you can do. Then we installed the Python and the pip. We upgraded pip. That was what we did in the handwriting Docker file. And we did it actually here too. We upgraded and installed the software that we needed. We ran apt-get install and apt-get update to do those updates. And so we got the latest versions of those containers. And then we copied the requirements and we installed all the requirements that are in the dependencies to build up those different images. And that's what you see when you actually go to the Docker image. You can see the different layers of a particular build in a different volume. If you click on a volume here, you can see the container that's in use. This is the OpenDevin. And you can actually inspect the layers that are comprised in that particular container. That's useful for just seeing the internals of how these containers and these images work. So here's our Bath University handwriting container, for example. If I just click into that image, you can see the different layers now. 14 layers basically constructed to produce that Docker image to automatically recognize the handwriting. So that's how it's all constructed. What about data persistence? We've talked a little bit about that. When you delete a Docker container and it no longer runs, it destroys everything in that container. Often we want to persist data between sessions. So I used a mounted drive. That's why when you see here, I was actually working on the /mnt work Bath and Docker. So I'd recommend you create a mounted drive which your Docker images can share and mount that into the image. And then you can read and write to that before the objects are destroyed so that you can then load up a new Docker and it will persist from that old data. Okay, so that's a persistence drive. Again, for efficiency, it might not be a bad idea to have that as a local drive. So this is on my C drive, just for faster file access and faster file copying as well. It can be used to share and persist data between containers, and it can be created in a Docker file or via CLI. Okay, so enterprises are looking to Docker for critical transformations. 80% say that Docker is central to their cloud strategy. 3 out of 4 companies have said top initiatives are revolving around applications and modernizing application infrastructure, and 44% are looking to adopt DevOps. This is in 2016, which is an incredible 10 years ago. I can confirm this trend has definitely taken place. And even now, people are talking about Dockerizing and containerizing existing legacy applications and transforming their infrastructure. Because Docker delivers agility, portability, and control. People estimate you can do 13 times more software releases by deploying to Docker containers. You can configuration control your Docker files as code, so it's perfect for infrastructure as code. You get a 65% reduction in developer onboarding time. If you give someone a Docker container, they're no longer messing about because something doesn't work on my machine and it should work on yours. What dependencies do you have? All of that is taken care of by Docker. So we eliminate the it works on my machine issue. And we have more control over our infrastructure, and we see a 10x reduction sometimes in maintaining existing applications. And this was also a study from Cornell University in Q1 of 2016. And again, these numbers are validated time and time again, just because of the efficiency gain that we get when we deploy Docker. And so one platform delivers one journey for all applications. We containerize legacy applications. That's called lift and shift to give us portability and efficiency. We transform legacy to microservices, looking for shared services to transform. And we accelerate the development of new greenfield applications and innovations when we use this technology as well. So this just reflects and recaps on Docker Compose to run multi-container Docker applications. We've just built 2 Docker images. We could actually now combine that. If I just go back to the command prompt, you can do a Docker pull. I think we did this already to get the latest MySQL containers. And we could do the same for WordPress. And then we could do a Docker run to pull those 2 together and run an image called WP. That could be our WordPress image, linking the database of WordPress and creating our own VM or Docker image that would then have all the dependencies needed to run WordPress. In practice, of course, you wouldn't put a root password like this. You would actually store that in a vault, in a DevOps style vault. We will talk about that kind of deployment issue in the DevOps lectures that are coming after this particular lecture in Docker. We can also see that we can abstract these commands into a YAML file. YAML is basically the language of DevOps, and just as we have code as code, we have tests as code, we also build our infrastructure as code. And so we can translate our Docker files into YAML files, specifying artifacts and properties such as port number, dependencies, access credentials. In this way, again, we will cover that in more detail in the actual deployment of Docker within a DevOps environment in the DevOps lectures. And then we can also use Docker PS and up and stop to control the running of our images. We also can do that from our Docker desktop version. We can actually stop and start Docker containers by hand, and also monitor their CPU usage. So there's a lot of jobs at the moment for managing DevOps infrastructure, container infrastructure in this way, and just seeing if there's any ways we can optimize those DevOps containers and Docker containers. That's important if we're doing lots of file operations, as I say, and lots of developers are using those containers and those images. So Docker Swarm is how we set up a basic Docker cluster. Docker Swarm is, if you go to playwithdocker.com, you can set up a swarm and you can join that swarm and connect Docker nodes together. This is also something you might do in a cloud deployment of Docker. We will have a dedicated lecture on how to deploy Docker in AWS and in Azure DevOps. But for now, think about this as a system of systems. You have different containers running a voting app, results app, a database, a Redis, and a worker. And now you're bringing all of those elements together. And you would do that in a Docker Swarm, ideally. Here's a curl command that will give you that example voting app as a Docker stack, which you can then run. And then you can spin up the cluster with Docker stack deploy on that YAML file, and then start the voting application. So that's kind of a system of systems. I'll leave that as an exercise for you to try. How do we get started with Docker? Well, we've seen some initial commands to get building. Docker comes with WSL. Also, if you're in VS Code and you've got a terminal on Windows, you can also see that Docker's pre-installed, and you can install it as an app into Windows. So you can run it from within VS Code, terminal, or WSL, as we've seen. You can install it via curl to get the latest Docker and pipe it to SH to install on Linux. You can also test and install experimental builds using these two commands here. And you can also install it manually by going to docs.docker.com and following the installation instructions. Docker for Windows is in existence. It's officially in beta, but in practice it's being used a lot, and it's just as stable and just as effective as running on Mac. On Windows, Docker uses Hyper-V, the inbuilt hypervisor, and Docker for Windows requires at least Windows Pro 10, Enterprise, or Education version. You have full API compatibility with Docker on Linux and WSL and on the Mac as well. And it deeply integrates with the Windows operating system for increased stability and speed. Docker for Azure, as we say, or AWS, we'll look at as a separate topic, but you can very easily deploy Docker as a swarm cluster and scale it up, scale it down. So we'll look at how that connects with the DevOps infrastructure, Terraform, Kubernetes, and Docker all working together in the cloud to deliver, for example, load balancing in an AWS setup, how to spin up VMs, how to spin up build agents in GitLab or GitHub. That topic is for another day when we will look specifically at DevOps, and Docker plays a crucial role in that. So Docker plus Windows Server is basically a Windows container. That's basically the infrastructure that we've been running today. Deep integration, 2 or more years of engineering collaboration between Docker and Windows. Microsoft is a top contributor to the Docker project, and a Docker maintainer. So they've invested heavily in both time and their energy and infrastructure to making Docker work on Windows Server from 2016 and later. So you can run Docker on Windows. As I say, probably the best platform that it will run on is Linux. It's kind of built for command line and fast deployments, and built on the Linux stack more than the Windows stack. How do we get started? Just like before we can learn to run, we have to learn to walk and jog first. Start by walking. Just set up your preferred Docker environment. Use some pre-built images like nginx. You should just be able to go to your command line console and do docker pull nginx. That's nginx if I've got that set up. Now here I'm actually in the container, which is a simple mistake to make. So just exit the container and docker pull, and you should be able to do nginx from outside that container, and you'll see this kind of thing happening quite a lot, especially when you haven't pulled a container recently. It will go down and pull the latest images for you to use locally. Same for common tools like MySQL, Ubuntu, WordPress, all of that kind of thing. I've also got an AI agent that runs in its own Docker container. So if you go to my container registry here, you may have seen it that I'm running OpenDevin, which is an AI agent that is running on a local host on my machine. So if I go back here, I can actually go to localhost, port 3000. And here I have an available agent that is actually delivered as a Docker container as well. So I'm going to show you that as a teaser for next time. And we're also doing 2 lectures on the AI-enabled software engineer. And this is kind of a precursor to that. But if I go to Docker and go through my previous commands, this is the Docker command that runs that container that contains an AI agent. A little bit more complex than the Docker commands we've used so far, but I'm basically running a container. I'm always pulling the latest, and the image is docker.allhands.dev. So that's the container registry that I'm pulling down, and you can see I'm pulling down a container that is convenient. It has everything needed to run that AI agent called OpenDevin, and it sets up the hosting for me, and it sets up the port, and it names it as the OpenHands app. So you can see how Docker is also being used to deliver AI agents and other AI infrastructure, vectorized databases, RAG databases, all of that you can deploy via Docker. In fact, I would recommend you deploy it in that way and make it available. So you can see how exciting this technology is. It kind of links my old school stuff like C++ testing and stuff. I can create containers that will do that for you. I can create containers that will run AI models. I can create containers that will run AI agents, and just run all of that seamlessly from one development environment. It's just like amazingly exciting. So learn to start to walk, try some pre-built images. Then we just jog a little bit. We can look at WordPress, build it for yourself. There's tons of blogs out there on docker.com and other communities. Ask ChatGPT for example Docker files. ChatGPT knows a lot about Docker. And then try it yourself. Extend your own walk solution, Dockerize your own projects. We would love to see Docker containers. We'd love to see you experiment with Docker Compose and Swarm mode as well, for you to deliver your projects as Docker files that we can then see. Also then go to github.com Docker Labs for more exercises, more practice, composing those Docker files with more complexity. The Europe 2017 DockerCon has all of the talks from Docker Conference from 2017 and later. And there's a Docker curriculum on the website shown at prakar.me that basically goes into more details than we've had time in this lecture. So thank you for listening. Hope this has excited you, this technology. Questions? I'm sure there are many. Head to Moodle. We'd love to hear from you. We'd love to hear your engagement. I'd love to hear your comments, sharing Docker files and Docker experiences, asking questions, and why not share your expertise with teammates and other colleagues and share Docker files as well. Of course, Docker can be integrated into Git. We've seen that. We've learned the motivation for containers. We've learned some simple Docker commands. We've learned to demo a real Docker deployment, and we've seen some examples of Docker containers running in action. So I hope that helps. I hope that's been interesting for you. Thank you for listening to this introduction to Docker. Please now head over to Moodle, have great fun experimenting with your own Docker containers, and we will see you next time for the DevOps lectures. Thank you and goodbye.